B. What I'd like to do today is just give some ideas about how, current set theory, well, in some sense, how it works, right? What I'd like to do this is give some examples of mathematical problems that set theory is these days able to solve. Right? And I think these will be, for me, these are a focus for what it actually means for something to be foundational. It ought to be something that can attack these problems. I'm not going to make any kind of philosophical talk during this lecture, because there's actually rather too many slides, more slides than I'd like here, but save that for the panel discussion later today. Yes?
It's July.
It's July? 6, 7, yes. Thank you. So there's an alternative universe, there's a multiverse, right? I stepped in the wrong... It's a typographical typo. Somebody already asked me, but these are oranges, right? You can ask me more about them later.
Not the only fruit.
Orange, the only fruit, yes. Is this loud enough? Can you hear this? Yes or not? Seems not. Nobody...
Yeah.
It is, okay. So tripartite talk. So as I said, there'll be a description of some problems on projective sets. And I'll be giving probably the most technical part of the talk is actually the beginning. I'll be just sort of defining things like the Burrell hierarchy and what projective sets are. And the mathematics kind of eases off in some sense towards the end, and then it kind of builds up again sort of from the last few slides. There'll be discussion in the middle in part 2 about large cardinals, strong axioms of infinity, how they affect the problems that I'm looking at in part 1. And part 3 is, well, for my own satisfaction, I suppose, is about some recent work on how you can think about reflection principles about the universe of sets to actually deliver the kind of cardinals you need in part 2 to solve the questions in part 1. So that's roughly the shape of how it's going to go. So the first slide here is about just looking at Burrell sets. And this definition you may or may not have seen before. And we think of Burrell sets as forming a hierarchy in certain Polish spaces. So a Polish space is just a complete metrizable separable space. And if you want, you can just think of this as the ordinary Euclidean R, or R to the n. Else you can think of it as Cantor space, 2 to the n, or bare space, n to the n. So discrete topology on the 2 or the n, and product topology on the whole space. So if you want, it's either R or it's the set of infinite sequences of natural numbers. Okay. Set theorists like bare space because any 2 copies, a copy of bare space is isomorphic to 2 copies of itself, or n copies of itself. So irrelevant questions about dimension don't really enter into it for us. Okay. So doing it for R and Rn is a little bit more fiddly, and you have to take away the rationals, but essentially bare space is isomorphic to the irrationals, so it's enough to consider either bare space or finite copies of it. So we start with the closed sets in T, think Rn or n to the n if you want, and this is then given a hierarchy. It's built up at the eth level. B eta, we look at unions of complements of sets that have occurred at previous levels. And this goes on all the way up through all of the countable ordinals, and the whole hierarchy kind of tops out at the first uncountable cardinal, omega 1. So B for Burrell, curly B here, this is the union of these Burrell levels on the way. Okay, I'm hoping that's all right. Any questions? Okay, analytic sets were essentially discovered by Luzin, and who did the early work on them. So an analytic set here, curly A, is the collection of sets A in your space, for example, subsets of R. So you could take a closed set here, or the beta-th level, the 0th level, or indeed something at any of the higher levels, and in a product of the space with itself, and you look at its projections down onto one axis. So so we may have some copy here of his bare space N. It's my T here. So what have I got? I've got a C here, and I just look at its projection down to here. And this is A. This is the typical A in my. So projection of a closed set or bare set down onto one axis. This is an analytic set. So famously, this came about. Luzin was correcting a proof of Lebesgue. Lebesgue had assumed that downward projections of a Burrell set in the plane were Borel, right, which wasn't true. Luzin realized that these were a different kind of set and corrected Lebesgue's mistake. So this was 1917. So, yeah. Okay. Probably his most famous result was that the Burrell sets are, so B, script B here, precisely the sets that are both analytic and have analytic complement. So Luzin then thought about sort of upping the descriptions here, and talked about thinking of a projective hierarchy. Right? So what one could do here is, as it were, take this picture again, if you like. One could think of, instead of starting with a closed set up here, one could start taking, well, an analytic set but in the plane, but actually that would project an analytic set. Take the complement of an analytic set here, project that downwards, and he showed you got something in a different class. So the projective sets are obtained by finitely often taking something, projecting it downwards, taking a complement, projecting it downwards again. Of course, each time you lose a dimension as you go down. So if you start off with something in k dimensions, you can do this process of projecting, taking complements, projecting down k times. And as you go up, you get more and more complicated sets on the way. So he showed here you get a definite hierarchy, and these are the projective sets here. So proj for today. So there are many questions, of course, that you could immediately came to their minds about asking things about them. So Luzin showed that the analytic sets were Lebesgue measurable. So this was something that was known for the Burrells. He extended this to these new analytics. So the problem that then immediately comes to mind was, are the sets in proj Lebesgue measurable? And there's a famous quote here from Luzin in 1925 that this was an intractable question. He thought one does not know, and one will never know, whether the projective sets are Lebesgue measurable. And probably the reason for the pessimism was that the fact that any set of reals, is actually the continuous image of a Lebesgue null set. Right? So he thought that result means that these projection operations are just kind of intractable. We won't get any handle on them. I surmise, right? But the pessimism was striking. Okay, so I'm going to list here 4 or 5 problems or questions about these projective sets. Right? So property of bare. So you can ask if whether a projective set has the bare property or not. So that means it's going to have meager symmetric difference with some open set. Right? So property enjoyed by Burrell sets and analytics, but is it the same for things further up the hierarchy. The perfect set property, again here. Does every uncountable projective set contain a perfect set? If this was answered affirmatively, this is, says something. Perfect set has size that of the whole continuum, right? 2 to the Aleph 0, or the size of the real line. So in some sense, if you've got a perfect subset, for a class of sets, you've solved Cantor's continuum problem for that class of sets. Yeah. Okay, so uniformization problem, right? Again, going back to Luzin, 1925. What do we have here? We've got a product space, script X cross script Y, right? So this is a Polish space. So again, you can think of this as perhaps R, and this is Rn, right? And we've got a region in the plane, which is called P, here. And this is, again, of a certain class, closed, Borel, projective, whatever. And the question that we're asking is, can we uniformize this region here? So we'll say that a function P star uniformizes P if, well, we can present this picture here. So for every X, if there is a Y in the fiber above X, such that XY is in the region, so here's a typical little XY point, perhaps, right? Then this function P star will actually deliver for us some Y prime in the fiber over X. So the question is, can one do this? Obviously, with the axiom of choice, you can do this in a kind of trivial and uninteresting way, right? You can just look at the fibers and just pick one using AC. But that's not of any interest. Right? What we'd like is to have some nice way of finding such a uniformizer. Right? So I'll think of a uniformizing function, P star, I'll call that projective if its graph is a projective set in the plane, as we've given here. So state problem 4, uniformization property, and here. Does every set in, well, T cross T, or X cross Y, or R cross R, right, which is projective, does it have a projective uniformizer? Projective uniformizing function. Right. So, and some information towards that was sort of independently Novikov and Kondo, right, was that every subset of the plane which was co-analytic, so a complement of an analytic set, right, this actually has a co-analytic graphed uniformizing function. So there's a kind of tight relationship between the complexity of the set in the plane and the function doing the uniformizing. The question here, the problem here, is somewhat looser. It just says, perhaps I've got a projective set at some level of complexity after k many operations of complement and projection. Maybe I'm allowed to find a uniformizing function which is a bit more complicated than k many operations. Okay, are there any questions there? So these are often called the regularity properties. Lebesgue measure, Baire property, uniformization, perfect subset property, and so on. So as you can see, these would be nice things for analysts to have. One more, just thrown in for good measure, really. The Banach-Tarski paradox. Right? You can take a sphere, decompose it into necessarily non-measurable pieces, and you can reassemble it into two spheres of the same volume. Right? It's a well-known consequence of the axiom of choice. You could ask questions about those pieces. Right? So, can we take one of these paradoxical decompositions of a sphere, in R3, say, and could we say that those pieces, we know they can't be Lebesgue measurable, but could they be projective in some sense? Could we get them in a relatively easy process of complementation and projection? Or is it the case that the axiom of choice has to give us completely randomized looking segments to reassemble? So to summarize, I mean, I've just put down here these P1 to P5, the Lebesgue measure, Baire property, perfect subset property, uniformization. Here. So I've deliberately chosen here questions that are more closely related to analysis than crop up in usual kind of meetings like this. Is the first thing people always talk about is the continuum problem or the continuum hypothesis. And the independence of the continuum hypothesis is the first things that people latch onto. Of course, it's the first thing that Cantor latched onto. It's easily stated and a fairly clear thing to think about. But it's of a degree of complexity greater than these questions here. The continuum problem is a third-order statement, right? In third-order number theory. These are second-order statements down here. Right? And actually, although we famously, we have the independence phenomena for the continuum hypothesis, we'll see here that there are ways of thinking about these problems here which so that they actually have answers. So by reducing that complexity to something nearer what analysts are thinking about, we can actually find some solutions. Whereas the continuum hypothesis, of course, is as far away as ever. Okay, so still some more history here. So despite, I guess post-1925 or post-Novikov-Kondo, there wouldn't have been, or at least in the history books, has come down to me, not so many theorems about projective sets. But Gödel's universe of constructible sets, which is used for this result here, is basically saying that the consistency of ZF will give us the consistency of projective set that's not Lebesgue measurable. So, again, a diagram you may be familiar with. Set theorists think of the universe as being some kind of V or cone-shaped thing. The ordinals here run up the middle. So the ordinal, being an ordinal, is a determinate property. It's a transitive set, which is well ordered by epsilon. So the ordinals come up here, and we think of the V hierarchy, or the sets of the rank hierarchy, is given by the Powerset operation at each stage. And as I think has already been said at this meeting, what Gödel did was carve out a potentially smaller universe inside of V, which was constructed in a very regular fashion. The regularity of that fashion meant the axiom of choice was true, and the parsimoniousness of the operation at each stage ensured that, for example, the continuum hypothesis was true. Very few sets are put in at each stage. We can think of it as the minimum amount thrown in with the ordinals in order to get a model of ZFC in here. So Gödel took, as it were, the definable power set at each stage, right, to build L. So if you look inside L, the well ordering that is there inside L enables you to calibrate precisely at which level sets start becoming non-Lebesgue measurable. Right? So there's a projective set that's not Lebesgue measurable. Indeed, there's a delta 1, 2 in the nomenclature for such a set. And this model L also then gives an answer to these other problems. Right? So there's a projection of a co-analytic set, PCA, projection co-analytic set, fails to be Lebesgue measurable. So this gives a negative answer, in a sense, to problem 1, just in terms of what's consistency strength. Right? It does the same thing for the Baire property as well. It's PCA set without the Baire property. And it shows, yes, so there's a paradoxical decomposition of the sphere, Barnard-Tarski paradoxical decomposition, again using PCA pieces in here. And likewise, again, inside this constructible universe, there's actually just a co-analytic set, a complement of an analytic set. It's uncountable, but it doesn't have any perfect subset in there. Okay, so this gives some restrictions on what could or could not be true inside this constructible universe. I think, as Myrna said yesterday, most set theorists think that this construction is too parsimonious. The idea that sets are being built up by some power set operation, there's no reason that intuition about sets should coincide with a logical intuition about semantics and definability. So we think these come apart. Right? And L is thought of most usually as being some smaller part of the universe than V. We see no real reason to think that the definable subsets give us everything. So I want to tell a different story, right? Are the principles that give a fuller picture of these regularity properties, right? And by Gödel's results, these must go beyond ZFC. And as Nathan introduced in his beautiful talk this morning, right, assumption on determinacy of infinite games can deliver for us gives us results here. Now, there's an early clue to this, a result of Solovey's. Right? So if you recall where we were getting failures of Lebesgue measure, for example, was at the PCA level in the Gödel universe. Right? What Solovey showed is that if you've got some ultrafilter, some non-principal ultrafilter on a large set, or if you like, a less than kappa additive two-valued measure on some uncountable set, some uncountable kappa like this, then actually you'll get the Baire property for PCA, Lebesgue measure, and this perfect subset property. So the thing to wonder about here, right, is that one can show that this kappa, were such a kappa to exist, it would be something right up here. Right? So this is kind of astronomical distances from where the reals live, which is all down here. So the real numbers live down at V omega plus 1. Right? Subsets of the reals are at V omega plus 2. Right? So whether that subset of the reals is Lebesgue measurable or not, it's a question about V omega plus 2. So the question you should be asking yourselves is, if this thing here is this strongly inaccessible cardinal, right, how's this affecting this down here? And the remarkable thing is that this indeed happens. Right? It's mainly about, the short slogan is it's about representation of sets on trees. Right? So just as Nathan was saying in his talk, for determinacy one needs more replacement and more power set. Essentially, this is because to get the determinacy of Burrell sets, one wants to try and reduce the complication of a Burrell game to an open game in a larger space. And this requires bigger trees and bigger sets. So what you do here in this argument is somehow give a description of PCA sets as trees on very large spaces. So mathematical result, but it connects high stretches of the universe with things right down at the bottom. So the next couple of slides just give the same kind of intro, I think, that Nathan was doing. For example, let's just take a subset of a bare space here, A a subset of n to n, or it could be a game on some other x to the n. And we define the game GA as indicated. So what we have is 1 is going to play something, and then 2 is going to respond. It's a perfect information game. Each person sees the other's move. 1 plays K1, 2 responds. Then 1 plays again a K2, and then 2 responds, and so on. So it's an infinite game, and 1 is deemed to win if the sequence of the K's ends up inside the set A. Otherwise, 2 wins here. And the game is determined if one of the players has a winning strategy. Right? So these are, I think, somewhat unfairly called Gale-Stewart games, but I think, as someone was remarking in the audience already, these were studied by the Polish school between the wars here, principally Barnach, Mazur, and various other people. Continued to be something that was important to the Polish school, even in the post-war years as well, in the 50s and 60s. There will be some references later. So set theorists have known for a while how to extend the ZF axioms in order to get the determinacy of games here for A in these projective classes here. And what's done is extending the clue of Solovay. Right? Further assumptions about large cardinals up here, or you could think of them as adding strong axioms of infinity to enhance the ZF axioms. These will give you more and more results about V omega plus 2 down here, and what is Lebesgue measurable or not. So essentially, if you've got determinacy for a class of games, you're going to get the regularity properties for them. Classes which are closed in some very, very weak or mild sense. So in particular, the class of projective sets here, if you've got determinacy for payoffs A, which are always projective, you'll get all of those nice regularity properties holding for the projective sets. Okay, so the problem then is, how are we going to get these strategies? Right? So it's not, nobody is going to pretend that it's intuitive that such a game like this is a winning strategy. For open games, where things are very simple, it's easy to give an inductive argument as to why an open set is going to have a winning strategy for one or other player. And even if you want to talk about unions of closed sets, this again is doable. But even once you start get beyond that, the next level up in the Burrell hierarchy, it starts to become increasingly difficult. And as Nathan said this morning, there were results that indicated that this was going to require more and more set theory, more and more instances of replacement and Powerset in order to work its way through the Burrell hierarchy. So the Friedman result that was there, which is a real tour de force in some sense. He showed that you were not going to be able to prove Borel determinacy without this use of replacement and Powerset. And he got it on the nose, right? It was exactly right in a level-by-level way as to how much you would need to get how much determinacy in each level of the Borel hierarchy. And the proof of Martin of Borel determinacy was something like 8 or 9 years later, after Friedman's result. But what Martin did before the Borel determinacy was something that in some sense is easier. He showed that actually analytic sets could be determined, again, by using the same kind of hypothesis that I put up there for Solovey's theorem earlier on. Right? So this would be called a measurable cardinal. Right? So if there's a measurable cardinal, which paraphrases this hypothesis here, then actually all analytic sets, games are determined. Of course, if a game is determined, it means player one has a winning strategy, for example, to win in it, then player two is going to have a winning strategy to play into the complement. Right? So analytic determinacy will imply co-analytic determinacy. And this was done using a method about indiscernibles. It used the inner model theory of L here. So it's a very beautiful result. And again, as I said, gave us these regularity properties for the analytic sets. Okay, and this was much earlier than his result about Burrell here. Okay, so on the other hand, to contrast with this, ZFC alone is not strong enough to prove the determinacy of analytic sets. So it cuts there between Borel and these projections of Borel. And this is simply because it's not a strong enough theory to prove this kind of determinacy. Right? We need to enhance the theory in some way. We can show that this is the case because from the assumption of analytic determinacy, you can prove the existence of, you can prove the existence in L, in Gödel's universe, of strongly inaccessible cardinals and things like that. So you can prove there are models of ZFC. So determinacy of analytic sets can prove the consistency of ZFC. Right? So we know we can't prove analytic determinacy just from ZFC alone. So to cut a long story short, right, after much effort, there were some kind of large cardinal that was distilled out by Hugh Woodin and called Woodin cardinals. It doesn't matter what those are. But if you've got infinitely many of these gadgets, then you can get the determinacy of all projective sets. So, and again, this went level by level. I mean, if you had something like n of the gadgets up here, you can get determinacy for n many iterations of complement and projection down here. So the existence of these cardinal numbers solves those problems about P1 to P5 and the Banach-Tarski and things for the projective sets. So the question then is, well, people say, well, do these cardinals exist or not? How do we justify these extensions of the axioms? And indeed, this is problematic. This is part of the ongoing discussion among set theorists, is how one can justify what appears to be this nicely well-ordered sequence of increasing hypotheses that we have. And these hypotheses tie up with various kinds of large cardinals in the universe. We're embedding properties of the universe to inner models, and then it becomes a set theorist's game. Right? Yeah?
Does projective determinacy also imply the consistency of some ZFC extended by some cardinal?
Yes. So if you have projective determinacy, then for each n, one can find an inner model with n Woodin cardinals inside it. Right. I mean, it can't prove that there are Woodin cardinals in the universe. And you can, if one thinks about it a little bit here, one can see why. I mean, here we are just talking about certain sets down at the bottom. It's almost impossible to think that these things down here could justify something about big sets up here. Whereas the other way around, that is possible because these big sets up here contain all of the previous things here. So the projective determinacy here is not going to imply that there are n gadgets like that in the universe itself, but there might be a thinner thing like Gödel's L in which there are n of these gadgets. So now we're on to the third part of the talk here, which is to think about, or to rethink about the universe of sets in a way that can deliver us some of these large cardinals. Right? So Gödel had extraordinary amount of faith, it seems, that large cardinals would settle questions such as here, or things about the Continuum Problem, for example. And he was of a person of a kind who, he was not a multiversist by any means. I mean, he thought of the ordinals and the picture that I've given here as being the standard orthodox universe. So he's often described as having some form of solid Platonism, either about mathematical objects. I don't think we need that for the discussion in hand. But as I said, I don't want to get into philosophical things in this talk here. So historically, so-called reflection principles, and I'll give an example in a moment, are associated with views that there's no one notion or statement or sentence that will kind of capture this whole universe of sets here. So reflection principles are usually formulated in some language, right? One thinks if some sentence phi holds of the universe, it can't be that it's only the universe that thinks this. It reflects down to some initial segment earlier on. If it didn't happen, there's some phi that's somehow capturing the essence of the universe. And one doesn't need to have a kind of theological discussion a la Cantor to think that this is a reasonable thing to be concerned, to hold true. Right? And what we're going to do is think about some global reflection principle which is going to overcome the principles to date, which are what I call intra-constructible. So the reflection principles that we'll discuss here are all ones that produce, they're consistent with being, the V being Gödel's L. Right? They don't produce any stronger principles than you get from assuming V equals L. Well, you wouldn't get any large cardinals that are not consistent with V equals L. Just some little bibliography here, strange place to put it, in the middle of the talk, not at the end or the beginning. So this was influenced by a paper of Peter Koellner, who analyzed new proposals for some reflection principles and showed again that they were consistent with V equals L or inconsistent. I'm quite influenced by Martin's paper here from this EF Exploring the Frontiers of Infinity. It's a Harvard workshop papers. And so I have a kind of mathematical response to Koellner here, giving these global reflection principles that I'll just talk about. And there's a paper with my colleague in Bristol, I love Bristol mention, Leon Halston, which gives some discussion about the philosophical aspects here. So what we're trying to do is rise to the challenge to kind of justify set theoretic reflection principles that will ensure the existence of these large cardinals. Right? And it's sufficient to deliver these hypotheses of these like Woodin gadgets in the universe so these are things that we need for modern set theoretical practice. So just a little quick review here. So this is Montague-Levy reflection. This is 1959, 1961. It actually says that if you take an ordinary formula in the language of epsilon and equals, in fact, you do have reflection. It's actually a theorem, right, of ZF. that for any formula, you can find arbitrarily large betas such that V beta reflects the truth of the matter in V about its members. So it's correct as regards phi about its members. Right? So it's a theorem. Right? There's no assumptions there. If you want to talk about formalizing the satisfaction predicate, you can do that. And you could replace this phi here with all sigma n formulae at once. Okay? And you get something like this. A standard kind of exercise I give my students is to show, of course, you can't do this for all n at once. If you could do that, you could show that there'd be models of ZFC in ZF, right? Which, of course, we can't do. So informally, we can write for such classes here that V beta is somehow sigma n elementary in V. Right? So it's a theorem of ZF. We can do this. And then Levy and Bernays, they considered extensions of this. They allowed second-order methods, and they considered classes over V. Right? If you allow reflection on classes, then you can deliver some modest large cardinals. So let phi of D be the assertion that if D is a function from ordinals to ordinals, but for any ordinal alpha, the range of D on alpha is bounded in ON. Right? Okay, so this is a formulation of the axiom of replacement. Right? So we have this is true in V. Right? And what they would do is say, okay, we reflect this situation down to some initial segment of the universe. So for any D, we have this holding. So let's reflect this. So at some initial segment V kappa, for any D, we have this holding as well. So this is seen to be an argument for inaccessible cardinals here. But again, something consistent with V equals L. Okay, the strict ZFC set theorist will eschew such an argument because it's quantifying over classes, right, which are not all necessarily given as definable in definable over V. Okay. But Gödel, again, takes this idea of reflection seriously. So Ackermann's principle is not explained here, but Ackermann's principle is this idea that the universe is somehow ineffable, and we can't pin it down in any one simple way. So the absolute infinity is unknowable, and the strength of this principle increases as we get stronger and stronger systems of set theory. The central principle is this reflection principle in general, which presumably is better understood as our experience increases. As I mentioned, Peter Kellner looked at some strength and reflection principles of Tate. You can talk about higher order logics, but then you have to start being careful about parameters that you might put into these formulae. This can mess things up for you. Generally, I am against higher order methods to try and eschew even second order considerations as much as possible. But anyway, those principles were all seen by Kellner, shown by Kellner, to be consistent with the view that V equals L. It doesn't deliver us anything like these gadgets needed for projective determinacy and so on. So these are all motivated, again, on some kind of syntactic level. They're about taking a formula or class of formulas in V and showing that these reflect downwards. So if we're going to get anything more out of this ineffability and reflection idea, something has to give. Right? We have to think of something slightly more sophisticated. So the reflection principles generalizing Montague-Levy aren't up to the task of providing the justification for these large cardinals that we want. And again, just to recap, why are we after this, right? So here's a remarkable theorem of Woodin's. Right? If the universe was populated throughout its length by these gadgets, right, these Woodin cardinals, then this forcing method, which we use for constructing, for example, failures of CH or something like that in countable models of set theory. The theory of analysis, analytical truth, but more than that, truth in this inner model that contains all of the reals. So way beyond, so it's just first order, second order, alpha order truth about analysis. This theory can't be changed by Cohen's methods. So suddenly, how analysis looks to analysts has become frozen, right? At least as regards perturbations by Cohen's methods. So this is highly significant, right? Here. But this supposition that there are at least infinitely many Woodins or class many of Woodins, this is now pervading more and more papers and results in set theory, if you actually look here. So what we want is some kind of global reflection principle that will deliver this proper class of gadgets to us. So what we're going to do is kind of take a sort of almost naive Cantorian stance, right? And we'll think about the kind of absolute infinities that he talked about and identified. And I think he was kind of well aware of the so-called Cantor's paradox, and I think he even said that he knew something like Russell's paradox. He knew that the class of ordinals could not be considered as a set. Right? So we're going to take these inconsistent multiplicities, as he sometimes called them later on. He seems to use both terms. I think it depended on who he was talking to, actually. And we'll take script C here to be this collection of informally given, right, collection of classes. Right? So I'm not talking about a formalized version of this during this talk. So we think of the idea of reflection as being taking from the universe a set-sized part of it to represent the whole. There's no one thing or idea that pins down the whole universe. So we do that, and then the new part is thinking of doing that idea onto V together with its classes here. So there are shades of a higher order, process going on here. So we'll take this structure and just think that there's a set-size substructure here. So there's a small part of the universe that reflects the truth of the matter about VEC. So we'll take the universe. One can tell a mereological story, if you want, about the classes that are in here. They're the parts of V. We'll reflect that down to essentially an initial segment of the universe, a V alpha, together with its parts. So we'll take a substructure of the universe, which is set-sized, a subset of the universe, set-sized collection of these classes. And the elementarity here is relatively weak. It's just set quantification, but we use some variable letters to range over these classes that we've got. So it's just beyond first order, but not second order reflection going on here. So this is the idea that we've got here. The elementarity that we've got implies that we have to take for the C prime Ds whose intersections with alpha give us all of the alpha plus 1. So what we've got is that there is this initial segment, V alpha and V alpha plus 1, which is some sense this kind of set size simulacrum of V. And just to close up here, what we can do is think about this. Sorry, I didn't mention much about it. We think of this here as being we take this isomorphism here of this whole set size bit that we've got, and we collapse it down to this transitive V alpha. The inverse of this isomorphism, if you think of that as J, that's going to stretch subsets or the parts of V kappa up to the whole universe. But this allows us to define a ultrafilter. So it turns out a less than kappa additive two-value measure on the power set of kappa. And if you remember, that was one of the hypotheses that we were using earlier on. So we're in business, right? This gives us such a measure on such a large uncountable set here. Once you've got that this, I think alpha on the previous page has become a kappa here, what you've then got is that if V thinks that this kappa here is a measurable cardinal, it's just elementary to just say, okay, there must be unboundedly many of them throughout the universe. Right? If you've got one that's this reflection point, they're everywhere. Right? And one can ratchet up this argument to show that these cardinals are not just measurable, but they're of this Woodin gadget type here, which is, again, a standard set theoretical argument. Nothing new there. It's just the perspective, I think, is new. Okay? And that's now going to deliver us what we want. It gives us the projective determinacy here. It gives us the absoluteness of the theory of L of R, right? This can't be changed by co-enforcing. So in particular, the language of analysis, the truths of analysis are now fixed here. So the conclusion is, what we're getting here is a good mathematical theory of the projective sets by allowing ourselves to take as a foundational theory of classes more seriously and allowing ourselves to do the kind of reflection that I was talking about. Okay, thank you very much.
How confident are you that this global reflection principle is consistent?
Sorry?
How confident are you that this global...
How confident? You shouldn't read anything into this pause, right? You shouldn't read anything into this pause, right?
I'm reflecting on that.
It's actually much weaker than large cardinals that are widely studied. So something that's weaker than supercompact cardinals, if you've heard of these, or things called one-extendable cardinals. Our confidence of any of these large cardinals is, I mean, in some sense, it has an empirical content to it, right? I mean, we've not found contradictions from these kinds of assumptions. What we're finding is, again, empirically or heuristically, is that all of these large cardinal things line up, right? And one can build a nice, attractive picture of a kind of spectrum of different embedding properties. And this is not near the top of this list. It's like 2/3 of the way up, if you like.
Okay.
Well,
What's the ultimate purpose in looking for these reflection principles? If you say that there are some common large cardinals that are already stronger than what you're talking about, then are you hoping to find further reflection principles to justify those? Or are you using this notion of reflection to give more confidence that these are consistent? Why are you choosing to look at reflection if there are things already stronger than what you showed us today?
well, I suppose initially I was taken up with Koellner's sort of implicit challenge in his paper that all reflection principles park you firmly inside Gödel's universe. I read this and I thought, no, we have to be able to do better than that. Right? So this is my response, I mean, my personal response to Koellner is to think of some reflection principle that's going to give us larger cardinals. And what I was pleased with was, what I was gunning for was Woodin cardinals throughout the universe, and it works. Right? In general, people discussing foundations of set theory often like reflection principles. Philosophers will discuss quite readily reflection principles in terms of the logic we use to discuss sets and so on. So couching what we're doing here in terms of reflection principles, again, is speaking to that audience as well. If I just gave you a definition of what a one-extendable cardinal was or something up here, 2/3 of the audience are asleep, right, within 10 minutes or something. But if you talk about reflection principles and this idea of the ineffability of the universe, which is an idea that's occurred, through the decades, I think you're connecting with that tradition as well.
When I read Körner's, I think PhD thesis, so he was, as you described, he was looking at these reflection principles, and they usually turn out to be comparative. V equals L. But then Tate's way of doing this with higher order parameters,
yes,
you all of a sudden get an inconsistency.
Yes.
And I found this a little bit unsettling, and I wasn't too satisfied with the resolution of, whether there was a resolution of this situation where you could easily dismiss these higher parameters. So do you have an explanation for why you don't want to go there?
I don't want to go there personally because I want to eschew higher order methods. I don't think it makes much sense to quantify over classes over V. I think of V as the domain of the mathematical objects. Mathematics takes place inside V. Parche considerations of large categories, that's another discussion. But the higher order principles, second order, third order, these are talking about one has to have a domain to quantify over, if you want to quantify over all classes. And I wanted to be deliberately vague at this point about saying what went into this script C, the collection of my classes. I don't quantify over that C, right? I don't go second order. There's just one second order statement that there is this substructure there, and that's it. And the rest of the elementarity of the substructure is first order. So I don't think there's anything very coherent about third order set theory or second order set theory, or at least I'm less convinced of it. So I just don't want to go there. The things that Körner was ruling out of order with Tate's principles were all third order and above. I think that was the case, third order and above. And we did already know that there were difficulties with third order parameters if you were going to go down that route.
There was a question?
So if you are already prepared to accept the existence of infinitely many Woodin cardinals from the point of view of consistency, what would be wrong then with simply taking ID? So taking ZF plus ID as
AD?
V? Yes.
It contradicts choice. Right?
Sorry?
It contradicts choice.
Yes.
Mathematicians are loath to give up choice. But, I think if you go down the corridor and talk to your native mathematician, they will want to keep choice.
But so these are social reasons, but do you see set theoretical reasons then why this would be wrong?
I think the view is that we don't necessarily have AD is about the reals and sets of reals. If you look at the Gödel universe that starts off with all the reals, as opposed to the empty set, this was the L of R that I referred to somewhere or other. Then here we go, L of R. This is the Gödel universe where we throw all the reals in at the bottom. So this is a laboratory for analysts. Now, R doesn't necessarily have a definable well order of its own, so this universe choice can fail in this universe quite easily. And that's how we can get the axiom of determinacy, and we will get the axiom of determinacy holding in this universe. I think if you want to talk about an AD world, or the desirability of taking AD as an axiom, then this is the universe you want to be thinking about, right? L of the reals. It's about the reals. I don't think there's a need to have AD in the whole universe when we can just think about this laboratory here.
Okay, one last question, please.
So, hi.
Hi.
If I understand sort of the basic idea of the global reflection principle, you take these absolute uncompleted infinities, sets, ordinals, cardinal, maybe V itself, and then collect them even further into this thing C, and then you reflect back down. So I wonder the extent to which these could be considered collections, considering that they can't be completed infinities, and whether, if they aren't to be thought of as collections, certainly they're concepts, mathematical concepts we can have. And as we heard from James earlier today, we could think of types as being this sort of formalization of the idea of a mathematical concept. We know what it means to be in a collection of these absolute infinities, even if we don't, say, can't imagine them actually forming a collection, a totality. So I wonder what you think about the possibility that maybe type theoretic intuitions or maybe type theory itself could play a role in the justification of the practices of set theory.
Right. So lots of things there. I'm not entirely sure that, well, we'd have to clarify what you meant by completed infinities. But then the second part is just a confession on my part of complete, absolute ignorance when it comes to type theories. I have no feeling for the second part of your, the major part of your question as to how, type theories could help, or how we could think about formulating these things in type theories. We bordered a little bit on this earlier when we were talking about Borel determinacy, whether one could have, what would a proof of Burrell determinacy look like in some kind of type theory? I think for me, and perhaps for the panel discussion, is a foundational theory should at least be able to be within sight of addressing questions like this about projective determinacy, projective Lebesgue measure, projective Baire, and so on. But the determinacy that's there, this needs uncountably many iterations of the Powerset operation and replacement thereon, right? If this requires stacking up universes in type theory for the same length of a hierarchy, my first feeling would be, well, is this really worth the candle, right? Are we not just redressing something up as something else? But I really, I know, I couldn't really say anything much about type theory in this context.
I was thinking more specifically about the reflection principle. I don't know if that makes a difference, because...
Well, reflection principle, you're talking about the whole universe as opposed to just the V hierarchy up to omega 1. Borel determinacy is about V up to omega 1, or the necessary part of where you need to prove it. So much weaker than these projective sets, which are requiring all of these Woodin gadgets here. I don't know. I have no suggestions to say. Sorry.
Thank you again for your talk.
Good, thank you.